So what I'd like to do is to come up with a more quantitative or mathematical approach to these oscillations. So basically I want to come up with an equation which is going to give us the position, velocity, and acceleration with respect to time for each of these oscillations. So so what I said in previous lectures was that the motion of oscillations is sinusoidal. It could be written as a sine or a cosine wave. And so if I look at the motion of, say, a spring that's bobbing back and forth, so I extend this mass on a spring to a position, an amplitude A, away from the equilibrium position. So there's going to be some spring force pulling it back. That's the restoring force. Then what it should do is it should start at A, go to the equilibrium position, go to minus A, and then go back through the equilibrium position back to A, and just go back and forth this way. So I said that we could do this. We could write this down as a. If I want to look at the position versus time, then what we'll have is a wave like this, where it starts at a position of A and it travels to a position minus A. And in this case, since we're starting with a starting position of A, then we need a function that x is equal to A at time equal to 0 seconds. So it turns out this function is the cosine. So x is equal to A times the cosine of some argument, which I'll call question mark. We'll get to the question mark in a minute. Or really, it's some function of time, right? And so what we could do is write this down as x is A times the cosine times the time. If we put in for time, so t equals 0, then at t equals 0, x is equal to A cosine of 0. If you plug that into your calculator, you find out that the cosine of 0 is 1, and so x is equal to A. Now there's a problem because the time has a unit in seconds, but the cosine, like the sine, like the tangent, like the cotangent, all those trigonometric functions, they want dimensionless quantities inside as arguments. So I can't take the cosine of 10 seconds. That doesn't make any sense. The argument inside a trigonometric function should be either in degrees, which is not really a unit, or in radians, which is also not really a unit. So we want something that is basically in radians. Let's try and put it in radians. And so what we can look at in our cosine function here is that if I start, say, right here, and I end right here, then what I have is basically one full cycle. After that, it's just a repeating pattern. It's the exact same thing every time. So what we can do is we can look at something called, well, in this case, it's the time. So what we're looking at is the period, t, is the time it takes to go from one position and then go through one full path or one full cycle back to its starting position. So that's pretty good. So the time it takes, so or basically what that means, and also if you look at this, what I've gone is gone from 0 down to a minimum, up to 0, back to a maximum, and back down to 0. So that's as if I've gone through one full 2 pi radians, if we were to think of this in terms of angles. If you're marching around a circle, you've now gone 2 pi radians. So that means in 2 pi radians, then I will have traveled the time of t in a time of t which then gives me 2 pi radians. If I only want to go half that time, then I would have 2 pi times the time it takes divided by the total time of a period. So if I go half a period, then it would be 2 pi times 1/2, or I've gone pi radians. So therefore, this is the argument we're going to put inside that cosine function. So now x is equal to the amplitude times the cosine 2 pi any time, the time it takes, 1 second, 1 minute, 1 hour, divided by the period of my motion. So the period kind of sets how long it's going to take to go one full cycle. So it takes an hour to go one cycle, then that's the period. And t is any time we want. It'll be, half an hour, 45 minutes, an hour, 3 hours, 10 hours. But as long as we set the scale with the period, then we can figure out what fraction of the period where we are in the motion. So this is now our equation for the position. If we want to look at the velocity now is going to be the change in the position with a change in time, which, if you remember from kinematics, is the slope of our graph. And so if we're plotting a graph of position versus time, it's the slope. And so if I go back and plot my position versus graph time again, and then underneath it I plot a velocity versus time graph, like this. Now what I can do is take the slope at these various points. So when t is equal to 0, slope is 0. When t is at this minimum, the slope is 0. When t is at the maximum here, the slope is 0. So therefore, we're starting off with 0, 0, and 0. Now, at this time here, where the position is equal to 0, then the slope is going to be maximum negative. And at this equilibrium point of x is now again 0, but at this point, the slope is maximum positive. And at this point, the slope is max negative again. So that means if I kind of put this together, what I get is I'll do it in red. What I get is when x is at its amplitude, v is equal to 0. When x is 0, v is going to be either positive or negative a maximum value. Okay, so that means I start at 0, I've got negative maximum back to 0, positive maximum back to 0, negative maximum. So if I look at this function here, when t is equal to 0, then v should be also equal to 0. So now I need a function where t equals 0, v equals 0, x is at its amplitude, and when v is v max, right here, x is 0, and so the function I basically have is minus v max. Remember, I have to get that negative maximum slope times the sine of 2 pi t over the period. So while the position is a cosine function, the velocity is a sine function. And we can figure out what is Vmax. Well, Vmax is just going to be the angular velocity times the position. So the position at the maximum distance is a, and so in this case, what we would get is the angular velocity, basically, which we can write down as 2 pi times the linear frequency, which is equal to 2 pi a over the period. So you could write it down that way too, or we can just leave it as Vmax. And so now in the case of a spring, the acceleration is going to be the restoring force divided by the mass. So we use Newton's second law, F is equal to ma. So this means that we have minus kx over m, or minus km times the amplitude times the cosine of 2 pi t divided by the period. So if we were to generalize this, this would be minus the maximum acceleration times the cosine of 2 pi times the time divided by the period. So this is now very interesting, because what we have, if I can draw this out properly, so we draw out these position, velocity, and acceleration with respect to time. The position is a cosine function. The velocity is a negative sine function. Like so. And the acceleration is a negative cosine function. Like this. Which again makes physical sense, because if we look at something like the spring, then if the spring is at its amplitude, x is equal to a, the velocity is equal to 0, but the acceleration, 1, is going to be negative to move it in the negative direction. When the spring is now at its equilibrium position, x is equal to 0, v is at its maximum, moving in the negative direction, and the acceleration is now 0, because we basically have no change in the velocity yet, but eventually when the spring stops, then now x is at its negative amplitude, v is 0, it stopped moving, and the acceleration now is at its maximum to move it in the positive direction. So now it all kind of makes sense that why the position and the acceleration give the same type of behavior, only with opposite directions of their vector, and the velocity has opposite motion. When the position is maximum, velocity is 0, acceleration is negative maximum. When the position is 0, velocity is at its maximum, and acceleration isn't doing much in terms of slowing things down.